Okay, so for this video, we will be discussing the aldol condensation and addition and dehydration. I will be doing part A, Marissa will be doing part B, and will be doing part C. So the theory for this lab is an aldol condensation that consists of tautomerization of a ketone that bonds with an aldehyde through nucleophilic attack. After the nucleophilic attack, a base grabs a proton and the alcohol group leaves and produces water. The dehydration occurs spontaneously after the addition and is stabilized because the base is present. There are two conditions necessary to undergo aldol condensation to achieve a high percent yield in a pure product. The first one is you start with an aldehyde that does not have an alpha proton. The second one is you have to have a ketone that has a protonated alpha carbon on only one position. So for the equation and mechanism for the aldol condensation, the first part of the reaction is an aldol reaction, and the second part of the reaction is a dehydration, which is an elimination reaction that involves the removal of water or an alcohol molecule. Dehydration may be accompanied by decarboxylation when an activated carboxyl group is present. The aldol addition product can be dehydrated through two mechanisms. One, a strong base like potassium tert butoxide, potassium hydroxide, or sodium hydride in an enolate mechanism. Or two, in an acid catalyzed enol mechanism. Some key points to note is to obtain the product for the double condensation, there has to be double the amount of aldehyde than ketone. And because of resonance in the conjugated ketone, a substitutive amount of positively charged beta proton deshields the conjugated ketone more than the alpha proton. To distinguish between a para-substituted benzene ring and a mono-substituted benzene ring in NMR spectra, the beta proton is not superimposed on the aromatic signal. Next slide. So the techniques used in this lab was one, selecting a recrystallization solvent. And a little background is if the compound dissolves immediately, the compound is probably too soluble in the solvent to be effective. And if no solubility occurs, they heat the solvent to its boiling point. And if complete solubility is observed, cool the solution to start crystallization for about 10 to 20 minutes. The second part is the actual recrystallization. Recrystallization is a procedure for purifying an impure compound in a solvent. And first, place the solid to be recrystallized on a creased weighing paper and carefully pour it into an Erlenmeyer flask with 1 or 2 boiling stones.
So for the procedure, you're going to start with your unknown aldehyde and your known ketone, which in this case of our lab, the known ketone was acetone, and our unknown ketone was dibenzaldehyde. You're going to mix the ethanol with 2 molar sodium hydroxide, and it's going to mix for 15 minutes until we see it precipitate. And if it's cloudy, you're either going to heat it in a steam bath for 10 to 15 minutes or cool it in an ice bath for 10 minutes. In 2 test tubes, fill one with ethanol and one with acetic acid and fill those. Then you're going to use vacuum filtration and wash your product with cold ethanol. We're going to disconnect the vacuum and rinse it with more ethanol and reconnect filter again, and then we're going to repeat those steps, but with acetic acid. We're going to find a suitable solvent using the criteria that Jessica mentioned before recrystallization, and we're going to add our crude product to both test tubes. And to recrystallize, we're going to heat the precipitate with a little bit of solvent until it's boiling, and add solvent until it's completely dissolved. Then we're going to cool it with an ice bath and use a vacuum filter, then wash the solvent and try it. So for our data, the product was a solid, and it was the dibenzyl acetone had yellow crystals. Our theoretical melting point was 110 to 111 degrees Celsius, and our experimental melting point ended up being 103.5 to 105 degrees Celsius. The mass of reactants used was 2.0 milliliters of acetone and 0.80 milliliters of benzaldehyde, and we ended up getting 0.143 grams of dibenzyl acetone. As you can see in our calculations, the acetone ended up being the limiting reagent, and when we calculated it out, we ended up with a percent yield of 22.5.
All right. So taking a look at the IR, we can see 4 significant peaks from the range of 3026 to 3052. We see a weak, sharp peak, which is indicating a CH aromatic sp2 stretch. At 1648, we see a strong, sharp peak, which indicates a C-double bond O stretch. From 1572 to 1625, we see another weak, sharp peak, indicating a C-double bond C aromatic stretch. And then from 1447 to 1493, we see a medium, sharp C bond H aromatic bend. When looking at the proton NMR, we see 4 significant signals. Protons A have the lowest chemical shift due to being less deshielded by double bonds in the carbonyl carbon on either side. Protons B are more deshielded because the phenyl rings are closer, and protons C are also on the phenyl ring, causing it to be deshielded in downfield. Protons D are the most downfield due to the aromatic rings and has double bonds on both sides. When looking at the C NMR, we see a total of 7 significant peaks. We can say that the carbon A is the most downfield because it is deshielded by the oxygen atom, and the atoms around it, or the carbons around it, show the chemical shifts due to the benzene rings. So taking a look at the depth 135 and 90 CNMR spectra, it provides information on the number of hydrogen atoms attached to each carbon. Full decoupled 13C spectrum shows all carbon peaks, whereas department 90 or depth 90 and depth 135, or depth 90 only shows CH signals. Depth 135 shows CH3 and CH signals. They give a positive signal, and CH2 gives a negative signal. All the spectra here only show CH peaks because benzyl acetone only contains CH bonds. The aromatic peak shows around 130 ppm. Taking a look at the cozy NMR, we can say that protons B from the figure are coupled with protons C and protons A, and protons D are coupled with protons A. And that is our presentation for aldol condensation.